In this class, I'll explain about the concept of plane stress problems. So, in a three-dimensional stress system, we have learned that there will be six stress components at a point. So, six stress components at a point. So, there are three normal stress components: sigma x, sigma y, sigma z, and three shear stress components: tau xy, tau yz, tau zx. So these are normal or direct stress components. These are shear stress components. Totally, we have six stress components, which can be represented in the form of a stress tensor. So like this: sigma x, sigma y, sigma z. They form the principal diagonal elements. Tau xy, tau xz, and it is symmetric, therefore this will be tau xy, tau xz, and this will be tau yz, this is also tau yz. So you know that tau xy is the same as tau x, tau yz is the same as tau zy, tau zx is the same as tau xz. So these are the things we have learned already. So now suppose in some problems of elasticity, the dimension in the z direction will be very, very small. For example, I will take a plate problem. If you take a plate problem, it can reduce to a two-dimensional problem like this. So this is the plate, thickness is this much. So you can see that this can be considered as a two-dimensional element because the thickness is very small. In such a case, you will be having sigma x like this. This is sigma x, sigma y like this, and sigma z will not be there here. So that means only you will be having sigma x and sigma y. So sigma z, which acts in this direction, which will be 0. So this is very important. So there is no stress in the third direction can be neglected. That is the meaning. So sigma z is 0, sigma x, sigma y exists. And coming to this shear stress, you will be having shear stress tau xy. And here you will be having shear stress tau xy like this. So tau xy will be acting like this. So finally you will be having only three stress components. So tau xy exists, whereas the other two, that is tau yz and tau zx, they will be 0. So these six components will be reduced to three components. So in this case, the stress tensor, which is written as sigma ij is equal to sigma x, sigma y, tau xy, or tau yx. So tau xy and tau yx, they are same. So this becomes the stress tensor in the case of a plane stress problem. So in the case of plane stress problem, the thing is only sigma x and sigma y exist, only tau xy exists, but sigma z will be 0. So this condition actually we can apply by using generalized Hooke's law. So you know that by generalized Hooke's law, which I have explained in the earlier video, according to this you have the equations like this. So generalized Hooke's law gives the strain in three directions x, y, z by knowing the stresses. So epsilon x is 1 by E into sigma x minus of mu times sigma y into sigma z. Please note that here E is the Young's modulus of the material of the plate and mu is the Poisson's ratio of that material. So 1 by E into sigma y minus mu times sigma z plus sigma x, and the third one is 1 by E into sigma z minus mu times sigma x plus sigma y. Now if you apply these conditions, so these conditions to this, so you will be having, so here you know that sigma z is 0, so this term becomes 0, here also sigma z is 0, here also sigma z is 0. Now what happens if you simplify this? The first equation, epsilon x will be equal to 1 by e into sigma x minus mu times sigma y. Second equation, epsilon y is equal to 1 by e into sigma y minus mu times sigma x. And the third equation, epsilon z is equal to minus mu by e into sigma x plus sigma y. So these are the strains in terms of pressures for a plane stress problem. So for a plane stress problem, these are the things. Now here shear stresses also can be written. So shear stress, we know that it is given by tau xy is the shear stress. Corresponding shear strain is gamma xy. So if you want the gamma xy is tau xy by g, where g is the modulus of rigidity. And similarly, gamma yz is tau yz by g, and gamma zx is tau zx by g. So in this case, see, these two will be zeros. So this will be 0 in plane stress case. This also will be 0. Only this will be high. So gamma xy is equal to tau xy by g. So that is the shear strain equation. So the governing equations of a plane stress problem are epsilon x is equal to this much, epsilon y is equal to this much, epsilon z is equal to this much, gamma xy is tau xy by g, where the other three stress components, that is tau yz, tau zx and sigma z, they will be zeros. So this is how we can explain a plane stress problem. So in the case of a plane stress problem, the dimension in that third direction, that is z direction, is very small when compared to the dimensions in x and y directions like this. So this is your x direction here, this is the y direction, and this is z direction. Thickness is very small. So when compared to width and length, so it is a thin plate problem. So in the case of a thin plate problem, it can be taken as a plane stress problem. Now if you write the relationship, constitutive relationship, that means if you want to express the stress in terms of strain for a plane stress problem, so that is called as constitutive relation. So that can be expressed in the form of a matrix form. So you will be having sigma x, sigma y, tau xy in the LHS, sigma x, sigma y and tau xy. So these are the stresses for a plane stress problem. This will be equal to some constant matrix. So material property matrix, E divided by 1 minus mu square, E divided by 1 minus mu square into you have the matrix 1 mu 0, mu 1 0, 1 mu 0, mu 1 0 and 0 0, 1 minus mu by 2. So this is the material property matrix multiplied by the strain matrix, epsilon x, epsilon y, epsilon x, epsilon y, gamma x. So please note that the first one, this one is the stress matrix, whereas this entire thing is the material property matrix, which is constant property matrix, and this one is the strain matrix. So sigma is equal to E into epsilon in the case of a uniaxial loading case, so where E is Young's modulus. But here, since we have to consider the effect of the force in both the directions, x and y directions, Poisson's ratio also will come into picture. So if you want how to write this is, so if you want sigma x will be equal to, you just multiply these two. So E by 1 minus mu square into 1 into epsilon, so it will be like this, 1 into epsilon x plus mu times epsilon y like this, plus 0 into this. Like that we have to write sigma y is E divided by 1 minus mu square into second row, that column we have to multiply mu into epsilon x plus 1 into epsilon y. This is what we get. And the third equation is tau xy. Tau xy is equal to E divided by 1 minus mu square into the third one is this divided by this, that is 1 minus mu by 2 into gamma xy. So these are called as the constitutive relations. These three equations are written in the form of a matrix equation like this. So this is about plane stress problem. So if they ask you to explain plane stress problem, so you have to write this example and these equations you have to write. Similarly, we can have another type of problem called plane strain problem. So that is opposite of this. In the case of plane strain problem, what happens is the dimension in the z direction is very large. So please see the difference. Here the dimension in z direction is less compared to x and y direction. So whereas in the case of plane strain problem, dimension in the z direction is very large compared to the other two dimensions. For example, here we can take the example of a long strip footing other than retaining wall. So they are all or we can take a long cylinder with some liquid flowing within it. So all those can be taken as examples of plane strain problems. So second is plane strain problem. So similar to the plane stress problem, we can write the relationship for strain problems, plane strain problems. Here, so these are examples I can take. Long bodies whose geometry and loading do not vary significantly, whose geometry and loading do not vary significantly, do not vary significantly in the longitudinal direction, along the length, in the longitudinal direction. So then it is called as a plane strain problem. So for example, if I take I take a long strip footing, so it will be like this, length will be like this. So you can have the width and depth. So length is along this direction. You can see this is z direction. So z direction is taken as the length. Okay. X direction is taken like this, and y direction is taken like this. You can observe here that along this length is very large when compared to width and depth. So this is surrounded by infinite soil mass, something like this. So this is the soil mass. So in such a case, this problem can be written as a plane strain problem. Soil mass. So this is long strip footing. You can take it as long strip footing. This is an example of plane strain problem. The reason here is, so if you take the strains in the three directions as epsilon x, epsilon y and epsilon z, the epsilon z almost it is 0, because you know that strain is nothing but deformation in a particular direction divided by the original dimension in a particular direction. So this deformation in the z direction can be neglected, it is almost 0. So in the case of a plane strain problem, epsilon z will be 0 along the length direction are taken as z. So epsilon z will be 0, only you will be having epsilon x and epsilon y, they exist. Then it is called as a plane strain problem. In addition to that, you have gamma xy also exists. So this is the condition for plane strain. So once again, the other strain components will be 0. That means epsilon z is 0, gamma yz is 0, and gamma zx also will be 0. Tracing the difference between plane stress and plane strain. There tau yz and tau zx will be 0 in case of plane stress. Here gamma yz and gamma zx will be 0 in case of plane strain. So you know that this is one example. Another examples are, you can take a retaining wall. So the loading does not vary in the case of, because we know that in the case of a retaining wall, so it is subjected to, this is the retaining wall, cantilever type retaining wall, you might have studied that. So this retaining wall along the length, so this is the direction wall. The direction is this, x is this, y is this, similar to that long strip footing. So here, what happens? So this is subjected to, you can say, soil mass. Retaining wall is, this will have soil on this side. So soil will be there. This exerts some pressure on the wall. So this soil mass will exert some pressure on the wall. So along this direction, your strain is neglected. That is the meaning. So similarly, you can take a long pipe with some liquid flowing within it, or earthen dam. In earthen dam also, water will be there on one side. The loading of that water on the earthen dam, it don't vary much along the length of the dam. So that is why that direction is taken as the along the length of the dam. So this is the example. These are the examples for. So retaining wall, I have given one example, earthen dam, then you can have gravity dam also, and long cylinder, long pipe, you can take long pipe with some liquid flowing in between it. So these are examples for plane strain. So now we will see how we can write the equations for plane strain problem. So you have epsilon x is equal to dou u by dou x. So according to the strain displacement relation, I have explained earlier, epsilon x is dou u by dou x, epsilon y will be dou v by dou y, and epsilon z will be dou w by dou z. Of course here this is 0, in this case this is 0. Then gamma xy is dou v by dou x plus dou u by dou y. So this will not be 0, whereas gamma yz, which is dou w by dou y plus dou v by dou z, this will be 0. Similarly, gamma zx, which is dou u by dou z plus dou w by dou x, this will be 0. So these are the 6 strain components. Out of 6 strain components, in the case of a plane strain problem, this will exist, this will exist, and this will exist. Only these 3 will exist. The other strain components will be 0. So now, if you write the expression for sigma z, you can see here sigma z will be equal to, or I can write epsilon z is equal to, you know that from the generalized Hooke's law, epsilon z is written as 1 by e into sigma z minus mu times sigma x plus sigma y. So since this is 0, so what you can write here is, this cannot be 0, therefore sigma z is equal to mu into sigma x plus sigma y. If you equate this to 0, you are going to get this. So this is another relationship which is used for plane strain problem. So as I already written the constitutive relation in the case of plane stress problem, similarly we can write constitutive law or relation for plane strain also, which is nothing but stress is equal to some matrix, constant matrix multiplied by strain. So in this case, this is written as sigma x, sigma y, sigma, then you have tau xy. These are the 3 stress components. This will be equal to the material property matrix. Material property matrix is E divided by 1 plus mu into 1 minus 2 mu. 1 plus mu into 1 minus 2 mu, where mu is the Poisson's ratio, E is the Young's modulus of the material of the structure or the body, into you have 1 minus mu 0. See, this is how it will be having 1 minus mu 0. Second row will be mu 1 minus mu 0, mu 1 minus mu 0, and the third row will be 0 0 1 minus 2 mu by 2, 0 0 1 minus 2 mu by 2. So this is the constitutive relation. Here you have the strain matrix like this. So once again here, this is the stress matrix, this is attaching this material property matrix. Material property matrix consists of E and mu. This is the strain matrix. So you will get sigma x is equal to this multiplied by 1 minus mu into epsilon x plus mu into epsilon y, like that. So you have to multiply this matrix with this matrix. First element gives this sigma x, second row if you multiply by this you will get sigma y, third row if you multiply by this you will get tau xy. So this is how a plane strain problem equations are developed. So if they ask in the examination, distinguish between plane stress and plane strain problem, you have to write these equations with examples. So in the case of in some of the problems in elasticity, 3-dimensional problems can be reduced to 2-dimensional. That is the advantage. So I have given an example. If one of the dimensions is very less compared to the other 2 dimensions, that is z is in the direction of z, if the dimension is very less, in the case of a thin plate which I told, then it can be treated as a plane stress problem. So using for example, you may have to find the stresses around a circular hole in a plate. So in that case, that can be treated as a plane stress problem and it can be solved. Whereas if the dimension is very long in the z direction, along the length direction, so that the geometry and loading will not be varying much along the length of an object, then such types of problems can be treated as plane strain problem. Examples are long strip footing, retaining wall, upland dam, gravity dam, long pipe with some liquid flowing within it. So these are the constitutive relations. So please keep it in mind that in a general 3-dimensional stress system or strain system, you will be having 6 stress components or 6 strain components, out of which if you consider them as plane stress or plane strain, then along the z direction the stress and strain components will vanish. So those 6 stress or strain components will reduce into 3 components.